Hello everyone, I'm Kameda from Tohoku University, Japan. Magnetic skyrmions, which we abbreviate as SK in this slide, is a nanometer-sized spin vortex with finite topological charge N. N is the number of how many times spins are in a sphere, which is defined by this equation. Skyrmions are appealing for potential application to magnetic memories, such as skyrmion train memory or skyrmion MRAM. Typically, when the skyrmion is circular and isotropic, the inter-skyrmion interaction is known to be repulsive and to decay exponentially. The structure of skyrmion crystal, SKX, is known to be triangular lattice. This is observed by LTEM. However, recently, unconventional interaction and SKX are reported in some specific chiral magnet systems. For instance, when an in-plane magnetic field is applied, the interaction and SKX is found to be anisotropic. In the 3D cone phase, the inter-skyrmion interaction is found to be attractive. Although the attractive interaction is attributed to a three-dimensionally twisted tube structure, the general mechanism for the appearance of these drastic changes has yet to be understood. We noticed that in all cases, skyrmion is distorted. So we focus on the skyrmion shape in 2D model, and we aim to understand the general relation between skyrmion shape and interaction. Also, we predict the inter-skyrmion interaction and SKX structures by applying the relation to anisotropic 2D chiral magnet model. Focusing on the isolated skyrmions excited in ferromagnetic state FM, we derive analytical expression of the interaction. Please note that the background of skyrmion is a single domain. We put one or two skyrmions in a single domain to obtain the expression. In general, the interaction V of R is the subtraction of two skyrmion energy and one skyrmion energy, where R is the relative distance between skyrmions. When R is sufficiently large, we can approximate the solution for single skyrmion as the sum of FM state and the deviation from the FM state. The FM state is typically in the out-of-plane direction, and the deviation is typically in plane components. After some analytical calculation, we can derive approximate expression V up of R, given by this. This is the direct relation between skyrmion shape and the interaction. We show that the distortion of skyrmion indeed changes the sign of the interaction. First, we look at the circular skyrmion at the distance is 20 sites. Shown are two-dimensional profile of each term of the integrand and the y dependence of each configuration at a fixed x site. The left component, partial x sx times partial sx, gives rise to minus and attractive interaction, whereas the right component gives rise to repulsion. In this case, the right side is larger than that of left side, giving rise to repulsive interaction. Whereas in the case of distorted skyrmion, we show that sign changes. In this way, Sx expands and Sy shrinks, which are the same as that of y dependencies. As a result, the left component dominates the right one, giving rise to the attractive interaction. From now on, we numerically investigate the inter-skyrmion interaction using the 2D square lattice model and show that distortion indeed induces the attraction. Hamiltonian is composed of 4 terms, the 3 of which are the same as the typical model. The first term is spin exchange interaction. The second term is Jaroszewski-Morier DM interaction. And the third term is the Zeeman interaction. The fourth term gives anisotropy potential, magnetocrystalline anisotropy. Let's call this MCA. This time we choose 3 hard axes to be P1, P2, and P3, shown here. This choice means we consider O11 field. Writing MCA with spin vector looks in this way. The geometry under consideration is shown on the bottom. Here we show the attractive interactions appear in O11 thin film with MCA. The skyrmion configurations are found by combining Monte Carlo simulation and solving LLG equation. In our parameter setup, the skyrmion radius is about 10 sites. This is the whole view of the interactions, and this is the magnified view up to 40 sites. When the MCA constant A equals to 0, the repulsive interaction is reproduced. Similar interaction is found at A over B equals to 0.1. The magnitude of A is scaled by the magnitude of Zeeman energy. By increasing A over B, we find attractive interaction in this way. Dotted lines shown in a similar color are the approximate expression we have derived in the previous pages for each parameter. We confirmed that V up of R reproduces V of R when R is sufficiently large. When we further increase A over B, we find that the magnitude of attraction becomes as large as 0.1J. Increasing A over B shows similar behaviors. Notably, the attraction is as large as J when A over B equals to 2. This is the each component of spin vector when the attraction becomes large. Interestingly, the magnetic domain is formed between the 2 skyrmions. These are the domains of angle plus and minus theta from z-axis. Also, we can see that the area of Sx is larger than that of Sy, which is the same as that of previously shown skyrmions. The large V of R is due to the energy gain from exchange interaction in this part. To understand why the domain is formed, we plot the single domain energy at A over B equals to 1 on a unit sphere, describing the direction of spin vector. Blue color shows lower energy. So there are 2 preferred directions in the xz plane in a spin space due to the combination of MCA and Zeeman terms. This is why the tilted single domain is formed in a ZX plane. Detailed analysis of the single domain Hamiltonian shows that there is a threshold value A over B for the finite angle theta. This graph shows the relation, and we can see that the threshold is 0.5. Please note that there are 2 energetically degenerate angles, plus and minus theta. From now on, we focus on a specific parameter A over B equals to 1 and investigate the relative angle dependence of the interaction. At this parameter, the magnetic domain is formed between the 2 skyrmions. This interaction is for two skyrmions aligned along the x-axis. We also calculate other directions. To change the relative angle from 0 degrees to 90 degrees, we fix skyrmion 1 at the origin and systematically change the position of skyrmion 2 on a 2D square lattice. This is the angle dependence of V of R. The interaction previously shown corresponds to this part. When skyrmion 2 is on a red cell, it is repulsive interaction, whereas when it is on the blue cell, it is attraction. We found that the interaction is anisotropic and attractive when the relative angle is roughly smaller than 45 degrees. We note that angular dependence is almost the same independent of the value of A, although the attraction is larger when the magnetic domain is formed between the two skyrmions. Given that the large attractive interaction as large as J appears in some relative direction, we expect that the interaction may affect the SKX structure. Indeed, this is true, especially in the vicinity of the SKX-FM phase boundary, where the skyrmion excitation energy and the attractive interaction may be comparable. The resulting lattice structure is distorted triangular lattice. The distance along x-axis is smaller than that of y-axis due to the large attractive interaction. Interestingly, the domain between two skyrmions are expanded along x direction. This is the obtained phase diagram when we change the magnitude of the external magnetic field. Up to 0.66, the elongated triangular SKX is the ground state. The similar configuration is observed experimentally in a very thin chiral magnet field. By increasing the magnetic field, we found the 1D skyrmion chain connected along x-axis as an excited state. This configuration means that the skyrmions aligned in the x direction have lower energy than that of y direction. The chain of skyrmion is also observed experimentally. Let's look at the phase boundary of SKX-FM. The key to understand the boundary is the field dependence of the skyrmion excitation energy, delta E. This is defined as 1 skyrmion energy minus the energy of FM state. Usually, the 0 point of this graph corresponds to the phase boundary. In this case, this value is 4.625. But we already know that the SKX is stabilized at the larger field than this value up to 0.66. If we look carefully at delta E, it is 0.6J, which is the same that of attractive interaction. This new boundary corresponds to the magnetic field at which the energy loss of delta E balances with the energy gain from attractive interaction. So the SKX in the phase diagram can be divided into two regions. One is conventional case due to negative delta E, and the other is the new mechanism due to attractive interaction. That's it. Thank you for your attention. I welcome your comments and questions.